right, folks, welcome to our final module of the course, Gaining Visibility and Resolving Issues Using Cisco Meraki Tools. In this module, we're going to focus on visibility and troubleshooting using very powerful Cisco Meraki tools. At a high level, managing an enterprise network isn't really about just configuring devices. It's about being able to see what's happening in the network at any given time, and more importantly, being able to quickly figure out why something isn't working. In kind of your traditional environments, troubleshooting means that you have to go into different devices, you have to use different tools, maybe a command line interface or SNMP monitoring systems, packet captures, and so on, and you're trying to take all of that information that you're gathering and you're trying to piece it together, which takes a lot of time. And a lot of times the issue is already gone by the time you're even looking. So what Meraki does a little bit differently, which of course it is different in this regard with just about everything we do, is a centralized dashboard. All your devices are continually sending their telemetry data, the client data, application usage, interface stats, RF metrics, and the system correlates that into a single usable view. So instead of knowing that something is broken, we can see which client is impacted, what application is affected, where the path issue is occurring, right? Specifically in the path, right? Being able to kind of isolate that issue. And that's really the goal here. We're trying to reduce the time to resolution. And ideally, we're trying to identify issues before even the users understand that there's some sort of issue. So as we go through this module, we'll look at the specific tools Meraki gives you, client timelines, event logs, packet captures, performance analytics, and how we can use them in a structured troubleshooting approach. We have troubleshooting methodologies, we have logging capabilities, the Cisco Meraki Security Center demo that you can take a look at, wireless troubleshooting. We're also going to look at exploring different wireless troubleshooting tools in a demo, looking at troubleshooting Cisco Meraki cloud application performance, and then we'll look at troubleshooting the Meraki Auto VPN. Then we have another demo exploring the VPN status, the firewall and static port forwarding demo, which we'll take a look at, and then the local status page. And then we have 3 different discoveries that we'll take a look at. Discovery number 30 in our course, troubleshooting an offline device. Discovery 31, troubleshooting content filtering, and Discovery 32, troubleshooting remote site connectivity. All right, so let's get started. So the first thing we're going to take a look at is different troubleshooting methods. Troubleshooting methodology is where an engineer is able to kind of separate themselves from people who maybe don't have a lot of experience, they don't necessarily know a structured approach to troubleshooting, and they want to just kind of poke around in the network and shoot from the hip to see if they can find out what's happening in the network. Troubleshooting is not random. It's supposed to be a structured, repeatable process. So if something breaks in the production network, you're dealing with multiple layers. Layer 1 through layer 7, if we're talking about the open systems interconnect model. You're also looking at distributed control planes, dynamic routing and forwarding decisions, and potentially thousands of different endpoints that you have to manage. So without a methodology, it's very difficult to effectively troubleshoot. If an issue hits, maybe alerts are firing, maybe you're seeing some sort of SNMP traps, syslog message, maybe you're getting some webhook alerts, users are calling and complaining, maybe your dashboard is lighting up like a Christmas tree. Your job is to take all that noise and isolate the effective signal, meaning we're trying to identify the scope. Is it a single client? Is it a VLAN? Is it a site? Is it a global issue? We're also trying to identify the impact. Is there an impact to latency, to packet loss? Are we experiencing some sort of authentication failure? Is there an application issue? And then we also want to look at the time of occurrence. Time of occurrence is pretty critical because that allows us to do things like event correlation. One event led to another event and so on. So it's not an exact science. We do follow a structured approach, but there is no kind of quote-unquote right path every single time. Networks are stateful. That means they deal with flows. We have natting, we have dynamic routing protocols, we have sessions, we even have policy-driven aspects like firewall rules and scalable group tags for Cisco TrustSec, ACLs, and then asymmetric problems as well. Maybe we're having some sort of asymmetric routing issue. So the same symptom could be caused by a control plane issue with routing or maybe DNS, or maybe a data plane issue where we have drops in packets, or a QoS misconfiguration, or maybe some sort of MTU fragmentation issue, or maybe there's some sort of application layer problem. That's why methodology matters. We have to be able to narrow down the possibilities without making total guesses in the environment. So let's break down these in kind of more of a structured approach. If we look at top down, in this case, we're talking about the application layer down to the physical layer. We're going to start at layer 7. Is the application responding? Are we getting, maybe it's an HTTP issue, and we might say, are we getting any kind of HTTP response codes? Is there some sort of issue with a TLS handshake? We might move down to maybe some DNS resolution. Maybe we're looking at TCP sessions, or maybe even IP reachability, or all the way down to the physical layer where we're looking at the status of an interface. If a user reports an application issue, this might be the direction that we take. Or if it's a SaaS or cloud-based service that we're troubleshooting, this could be a proper approach. Bottom up is the opposite. We're going from the physical layer up to the application layer, meaning at layer 1 is the interface up. Is the data link layer up, right? Show IP interface brief in the command line or something like that. Similar to that concept. Are we seeing errors on the interface? Are we seeing cyclic redundancy check errors or duplex mismatches? We can look at VLAN tagging. We can look at routing. We can look at session information. We can even look at session establishment with the application. And that's kind of going up the stack from layer 1 to layer 2 to layer 3. Session establishment would be more like layer 5, and then the application would be layer 7. If we are noticing link failures, or maybe we suspect that there's a hardware issue, this is the appropriate approach. We also have a split the baby approach, divide and conquer, right? Pick a midpoint in the stack. Maybe do a ping or a trace route to test IP reachability. If the ping works, most likely the problem is kind of above layer 3. If the ping doesn't work, then we possibly believe, or we can kind of surmise, that the problem might be below layer 3. And this is really the fastest method in most real-world scenarios. We can also do a packet walk where we're following the path. We're trying to trace the actual forwarding path, a client, an access switch, distribution, WAN edge, internet, and so on. So we're using tools like traceroute, flow analytics, routing tables, forwarding information-based lookups, and so on. In Meraki, this actually maps directly to a topology view, which gives us that client path visualization. We need to also be able to spot the difference, right? If there are differences in what we've seen in the past to what we see today, maybe we have a good baseline of operations, or maybe it's just comparing something that's working versus something that's non-working, right? Maybe one client can get to a specific host in the enterprise and the other client can't. So now we can kind of do a comparison and say, what is different about these two clients? Is something healthy versus something unhealthy? What is the difference in that case? Is it normal versus degraded, right? So we can look at that from a perspective of maybe an internet connection or a WAN link. We could be looking for things like configuration drift. Maybe there's some sort of policy mismatch. Maybe there's some differences in the firmware that we have in our environment. So it's a really effective approach if we have a standardized environment. We can also move the problem. We can change variables, right? Move a client to a different VLAN. And if the problem follows the client, maybe it's not related to where that client was originally connected. We can connect to a different access point. We can switch a different WAN connection. If the issue follows the client, most likely then that means that the issue is related to the client itself. If it stays within the infrastructure, maybe that's a network problem. So how does Meraki enhance these methods? And this is really where everything changes from your traditional troubleshooting environment. Instead of manually pulling data from show commands in the CLI or SNMP polling systems or packet captures, we get what we call unified visibility. We go to client, we go to application, and we go to network path in a single view. There's no need to correlate across a lot of different tools. We also have native logging in real time as well as historical logging. The event logs are actually tied to clients, to APs, to switches, to security appliances. So we're not just seeing the logs, we're seeing logs in terms of context. All right, we can look at wireless health metrics, association failures, authentication latency, maybe some sort of DHCP or DNS breakdown, which is going to map from a layer 2 to layer 7 for troubleshooting for that wireless. We can also use Meraki Insight, which gives us information about application performance, tracking SAS performance, latency, jitter, loss, or looking for network issues versus application backend issues. We also have the ability to do VPN status and path monitoring. We can look at the state of our tunnels. We can look at SLA metrics. We can look at failover behavior. And then finally, we have the topology view, which is a visual representation of our forwarding paths. This allows us to implement that follow the path strategy, but instantly, right? The goal of these methods, whether it's classic or Meraki based, is to reduce our MTTR, our mean time to resolution, isolate the fault domain quickly, and move from the symptoms to the root cause as efficiently as possible. And this is where Meraki is kind of the gold seal in this case, because it can gather the data, it can do that event correlation, and it can even make decisions more effectively than what we see in traditional troubleshooting architectures. So now let's talk about the actual tools that we're seeing, right? The actual tools that we can use when we're troubleshooting. And we need to also look at maybe possibly the trade-offs between those tools, because in a real network, it's not just about what works. It's about cost, it's about operational overhead, and the amount of time it takes for us to get to where we're trying to get. We do have built-in tools like ping and traceroute and NSLookup. These are our first-line tools, if you will. Very fast, very lightweight, pretty much available anywhere. Ping is an ICMP-related tool that allows us to test layer 3 reachability and look for things like basic latency. Traceroute will allow us to see the layer 3 path and possibly where the failure is occurring within that path. And then we have our NSLookup and DNS tools, which allow us to validate the name, resolution. We can do layer 7 dependency checks in this case. But from an engineering perspective, we're validating the control plane correctness. Right? We're trying to confirm routing. We're trying to confirm ARP. We're trying to confirm domain name resolution, not the full data plane behavior. So a ping success does not actually guarantee an application success. It doesn't test ports. It doesn't test policies, and it certainly doesn't test stateful inspection. The next tool that we have on the list here is our protocol analyzer. That could be Wireshark or Switchport Analyzer, or maybe a kind of a different packet capture option. But this is packet level visibility. Here we can look at the TCP three-way handshakes, retransmissions, windowing issues, maybe some TLS negotiation issues or application payloads. This is really the most direct visibility to the truth that we're troubleshooting, because the packet is the packet, right? It's going to contain the real information. There is a trade-off. It requires a mirror configuration in terms of port mirroring, or it will require a switch port analyzer. It can be a little bit time consuming to analyze the data. You certainly need to have a deep understanding of how to look at protocols and gain protocol knowledge. The cost is relatively low, but the experience overhead is pretty high, especially compared to the tools that we just saw, the ping and the traceroute and NSLOOKUP. Simple network management tool. The Simple Network Management Protocol tool, SNMP, is a polling-based monitoring tool. So that will give me device-level telemetry over a period of time, looking at things like interface utilization, CPU and memory utilization, maybe looking at error counters, overall device health. That is trend-based visibility. Again, not real-time packet inspection. From an engineering perspective, SNMP is poll-based, meaning that we're polling and the polling intervals matter. We can actually miss transient issues or temporary issues between those polling intervals. From an operational standpoint, it's going to require those SNMP collectors to collect the information. We have our MIB, or our management information-based management, that we have to deal with SNMP. And we also have some tuning, right? We do need to tune the polling intervals in our environment. Now we're getting into one of the most powerful tools for traffic analysis, which is NetFlow, or IPFix if you're looking at it from a different perspective, but it's kind of the same thing. This provides us flow-based visibility. So instead of packets, we're getting everything about the conversation, the who, the ports, the protocols, the volume, the entire conversation for the application. So we can say things like, all right, well, who is actually consuming the bandwidth? What applications are active in the environment? Where is that traffic going? This is a lot more scalable than a packet capture, but it does require exporters. So those would be my routers and my switches. It will require collectors, and it is definitely going to add CPU overhead on our network devices. We can use a Wi-Fi spectrum analyzer. This is a layer 1 troubleshooting tool. We're looking for non-Wi-Fi radio frequency interference, looking at channel utilization, microwaves, Bluetooth, DECT phones, those kinds of things that might be operating in that ISM frequency, but it's not necessarily Wi-Fi enabled traffic. A lot of wireless issues are actually not network issues, they're radio frequency spectrum issues. But the tools here are pretty expensive. Hardware or software, you do have to be on site, in a physical site, to do the analysis. And again, this is a tool or a set of tools that would require quite a bit of knowledge and understanding. Then we have our network monitoring software, our enterprise tools. This is kind of where everything gets centralized. Platforms that aggregate things like SNMP, NetFlow, syslog, telemetry data, alerts in our environment. And it's going to give you that single pane of glass where you're going to have your dashboard and your correlation and your alerting, basically like a SIEM or some sort of SOAR system, security, orchestration, automation, and response. And maybe not necessarily specifically related to security, but a similar concept where you have your network operations center visibility. Now, all that being said, where does Meraki change this model? Instead of doing SNMP collectors, instead of having NetFlow analyzers, instead of building separate monitoring platforms, Meraki builds all of these tools into the dashboard. Flow analytics built in, client visibility built in, event logs and topology built in. So that's going to reduce our cost, that's going to reduce our deployment complexity, and it's going to reduce our operational overhead. All right. Now let's move beyond just seeing issues in the dashboard. Looking into exporting that telemetry information so we can do something like event correlation, retention, advanced analysis. Because in a real enterprise environment, Meraki is rarely standalone. It's going to actually include a lot of ecosystem partner equipment. SIEMs, for example, like Splunk or QRadar, network management system tools, security analytics systems, and so on. So let's start with syslog, the top right there. It's basically event streaming for our security and operations. It's your primary mechanism for getting those real-time events out of Meraki into those external systems. Think of this as push-based logging in near real time, but it is structured text-based alerting. All right? The Meraki devices that will actually generate these syslogs are our MX devices, our MR devices, our MS devices, and so on. The MX device is going to generate, that's our security appliance, by the way, and that's going to generate event logs based on general system activity. It'll generate snort-based threat detection logs through IDS and IPS alerts. For URL logs, we're looking at things like web filtering and content access. And then we have traffic metadata, very similar to NetFlow, where we actually get flow log information. So here we're getting security visibility, we're getting incident response, we're getting traffic forensics, and so on. If we go to the wireless access points, our MR devices, they're going to send most of the same logs. They're obviously not going to have IDS or IPS logs, but they'll give you things like client association events, authentication failures, roaming events, and that's useful for things like wireless troubleshooting or user experience tracking. The MS devices are switches. Those are limited to basically event logs only. Things like a port up or port down, maybe some change in the spanning tree protocol topology or with the spanning tree protocol environment, VLAN events, and so on. A lot less granular, but still good for things like layer 2 visibility, topology changes, and so on. Syslogs are event driven. They're not state driven. You're going to see what happened, but you're not necessarily going to see the current state. So the syslog is really good for things like what happened from a timeline reconstruction standpoint. Is there some sort of security event correlation that I can track with that as well? In the bottom right, the SNMP polling-based telemetry, right? SNMP is poll-based, meaning that we're periodically polling for information based on structured data in our management information bases, which is a way for us to navigate through a platform. SNMP is going to give you things like errors and utilization for interface counters. It's going to give you CPU and memory information, the device status, but it's going to give you the state over time. Not necessarily discrete events, just the state over time. Polling interval matters here. If you poll too slowly, then you might miss spikes. If you poll too quickly, you're going to get paralysis through analysis because you're going to increase your overhead. So, and it also does require most likely some sort of primary NMS platform, network management system platform. You would have to have the right MIBs aligned with the right pieces of equipment, and you would have to tune that polling and tune those logs and so on. Now we can do native versus external logging. This is kind of one of the most important architectural distinctions. In native Meraki logging, which is of course we access that through the dashboard, that's going to be cloud aggregated. It's going to be context based, client, device, application. It's going to be very easy to use, and it's going to be limited in terms of how long we can maintain that information based on our licensing. But it is good for real-time troubleshooting and for operational workflows. External logging like syslog and SNMP being sent to external systems, more so for long-term retention and maybe correlation across multiple platforms. So it's best for things like compliance, for security analytics, for historical forensics. If we look at, say, event logs on the left versus syslog versus SNMP, how do these all kind of fit together? The event log is our dashboard that gives us immediate visibility with context. Syslog is a detailed event stream for external analysis. SNMP, continuous performance monitoring and state monitoring, again, dependent upon the poll intervals, but we do really need all three of these to get that complete observability strategy that we're trying to get. Okay? User reports maybe an intermittent VPN drop. So what do? We go into our dashboard event log. We see a VPN tunnel flapping, right? That's not necessarily what we're seeing on this slide, but this is just an example. Maybe I then go to my SIEM, my security incident and event management platform, where I'm capturing syslog, and I correlate that with the IDS alerts or maybe possibly a WAN failover. Then I maybe look at my SNMP and my NMS logs. So I'm looking for WAN interface errors or maybe utilization spikes. And together, we can identify that root cause. We can look at the timeline. We can look at the contributing factors. And Meraki really does simplify that visibility. All right, we're extending that visibility outside of Meraki by using the syslog for events and SNMP for metrics, but correlating all of that in one place is very helpful. Now, let's step back into the security operations side of the dashboard, the security center. All right, this is where Meraki moves kind of beyond networking and into threat detection and response. The security center is like your lightweight SOC interface, SOC, Security Operations Center. It aggregates all of the telemetry from our snort-based inspections through IDS and IPS, our malware protection with Cisco AMP, our DNS layer security with Cisco Umbrella. So instead of looking at raw logs, we're getting correlated security events in a centralized view. Now, if we look at phase one, which is basically to monitor and identify, right? Phase one on the left, phase two in the middle, phase three on the right. On the left, we're talking about our visibility layer. We're looking at the latest threats. What are some of the most common attack signatures? We can even do retrospective detections, meaning that something that might not have been triggered as a true alert back then might now change its perspective. All right. That last one, actually, retrospective detection is pretty important. Let's say a file or a flow was originally allowed, right? But then later on down the line, we identify that as malicious, and it gets flagged at that time after the fact. So now we have cloud intelligence updates that allows us to go back and not just assume that because something was allowed previously, that it would be allowed in the future as well. We're not just assuming that. All right. We also have some key telemetry that we're analyzing. We're looking at events over time. That's trend analysis. We're looking at the most affected networks, the scope of impact, the most effective clients. We're trying to find maybe patient zero. Maybe we have the most prevalent threats that we're looking for, attack patterns or indicators of compromise. Maybe we're looking for operating systems that might be impacted by a threat, targeted behavior. So we're shifting from reactive troubleshooting to a threat hunting mindset. Now, if we drill down into phase two, which just happens to be called drill down, that's our deep inspection. Once we identify something is suspicious, we don't stop there. We have to pivot into this deep analysis. That means that we're trying to determine the origin, the source IP, the geolocation, the autonomous system number. We're inspecting flows or packets. We're trying to understand the attack type. Is it command and control traffic? Is it some sort of exploit attempt? Is it some sort of malware callback? So from an engineering perspective, we're correlating layer 3 and layer 4 flow data. We're looking at layer 7 signatures, and we're looking at our threat intelligence feeds. Networking is now merging with security analytics. There is a very important concept here, though. Not every alert is a real threat. So we have to distinguish between what's a signal and what is noise. We're going to see false positives. We're going to see benign traffic that's flagged as suspicious, and we're definitely going to see applications that are misclassified. So your job is to validate and then correlate and then ultimately confirm. Then our last step, take some action. Once we've confirmed a threat, now we move into containment and remediation. And with Meraki, we have direct controls to block actions. We can block specific IPs or destinations. We can block entire countries, geo-based policy. We can do whitelists, right? Maybe they're called allow lists now, where we're doing false positive handling, marking traffic as trusted so that we can reduce our alert fatigue based on those false positives. Our goal is always going to be to prevent the spread by applying firewall rules, isolating affected clients, modifying group policies. So let's say a user can't download a file, and the security center shows us that the advanced malware protection tools blocked the file. So now we're going to drill down. That file hash, which is how we identify files in AMP, was flagged as malware. So our next action is to verify that. We allow it or we block it based on policy. So our scenario is that we have suspected malware. We see repeated outbound connections to a suspicious IP. And this looks like a command and control environment because it gives us that pattern. So now our action is to isolate the client and then ultimately to block the destination. Or maybe we see an abnormal traffic spike. So we're seeing unusual traffic volumes from one host. Maybe this is a data exfiltration. Maybe it's a botnet activity. So now we apply a policy. We investigate the endpoint. There is a bigger picture here. It's not just the dashboard. It's layered security architectures. We have the MX, which is our enforcement point. That's our firewall, our IDS, our IPS. We have our security center for visibility and workflow management. We have our external SIEM for long-term correlation. So monitor, identify, drill down, take action. We're trying to reduce our dwell time. We're trying to contain issues quickly, and we're trying to prevent lateral movement in the network. That's what security operations are. Now, let's get into one of the most challenging areas in networking, wireless. This is the key difference. In a wired network, problems are pretty deterministic. In a wireless network, they're probabilistic. What does that mean? The signal strength fluctuates. The interfaces are unpredictable. The clients are inconsistent. So troubleshooting Wi-Fi is not just about the networking. It's about the radio frequency spectrum. It's about authentication. It's about client behavior. Wireless troubleshooting is, in general, more difficult. If a cable gets unplugged or if an interface is down, that's easy to spot. But when a user says, hey, the Wi-Fi is not working, that can mean so many different things. It can mean there's no association because there's some sort of layer 1 or layer 2 RF issue. There's some sort of authentication failure with a pre-shared key or 802.1x. Maybe there's some sort of DHCP failure at layer 3. Maybe a DNS failure at layer 7 or application issues. Of course, in terms of troubleshooting, DNS and DHCP and application issues could exist in the physical world as well. But these are the same symptoms, they're just different root causes. Okay? Some of the common root causes that you might see would be like a client-side issue. somebody's using the wrong credentials, or maybe they have outdated drivers for their interface, or maybe their supplicant for 802.1x is not configured correctly. We could have authentication issues with Radius. Maybe the Radius server is not even reachable, or there's some sort of certificate validation problem, or EAP mismatch. Maybe we're having some sort of network services issue, like there's a DHCP scope exhaustion, or DHCP relay misconfiguration, or maybe some sort of DNS resolution problem. What's unique to wireless is layer 1, because now we're dealing with the radio frequency spectrum. So co-channel interference or adjacent channel interference, low signal to noise ratios, meaning that the signal is equivalent to the noise, right? If it was 10 to 1, that would be a high number. 10 signal, 1 low noise, that's a pretty good ratio. But 10 signal, 10 noise, now that's a low number. 10 on top, 10 on the bottom, SNR is 1. So that means that the noise is just as powerful as the signal. And that can be an issue. Of course, there's many other aspects to the radio frequency spectrum that we have to deal with. We have to deal with non-Wi-Fi interference as well. All right? Now let's take a look at this from the IT administrator inbox. From an operational standpoint, this is pretty important because most troubleshooting starts with a bad problem description. Hi, this is Todd from Marketing Department on level 6. I am connecting to an access point, AP6B, with my Windows 10 laptop. They're already providing, by the way, more information that we probably would get anyway. I've successfully authenticated via 802.1x, but I'm not obtaining an IP address, although I can see my laptop is sending out DHCP discoveries. Could you help me? You know, that's actually pretty good. I mean, it's not realistic, unless it's an IT person or some sort of IT expert, but we don't typically get that, right? What we get is an email message that says Wi-Fi is broken. All right. The trouble ticket identifies the user's location, level 6, the actual AP that they're trying to attach to, the device type. They're confirming that they're able to authenticate with 802.1x, and DHCP is being sent out, which means they're associating, but they're not getting an IP address. So based on an engineer or an engineering mindset, we can already narrow this down significantly. We know that the radio frequency is working because the client associated to the AP. Authentication is working because 802.1x worked. DHCP requests are being sent, so there must be some sort of layer 2 connectivity. So where is the problem? Most likely it could be a server-side issue. It could be some sort of DHCP relay problem. But that's the power of getting that good information. When troubleshooting wireless, you have to follow this order. Association. Did the client connect to the AP? Check your RSSI. Check your SNR. Check your channel. Look at authentication next. Are we doing PSK or 802.1x? Are there some radius failures? Then we do IP addressing. By the way, that's a very important thing to recognize about 1 and 2. Authentication happens after association. A lot of people think it's the opposite, right? I authenticate you first and then I allow you to connect, but we don't. We connect first and then we authenticate. Then step number 3, is there a DHCP discovered? Did we get an offer? Did we send a request? Did we get an acknowledgement? Are there issues with the DHCP scope? Are there reachability issues with the DHCP server? Is there possibly a rogue DHCP server that's submitting bad information? Then we can look at network layer reachability. Can the client reach a device within its own network? Obviously, if it's not getting an IP address, that's not going to be possible. But that's something we check. And by the way, that can be our gateway, because our gateway is an IP address within our own broadcast domain. But you can also check other clients within your subnet. Could the device reach another device in another VLAN or another segment in the network? Then we can look at the application layer, where we do things like DNS resolution, or maybe we take out DNS and we try to access a resource with its IP address. Maybe we suspect that there's some sort of DNS related issue, so we're trying to essentially establish the boundaries. We're certainly looking for things like application-specific failures. This is where the dashboard becomes extremely powerful. So we don't have to manually check controller logs or radius logs or DHCP server logs. We get that client-centric view that shows me the association status, the authentication result, my DHCP successes or failures, the performance of DNS, all in one location. Wireless troubleshooting is about breaking the problem into layers, and the fastest way to solve the issue is to eliminate the entire layer at once. So when you get a detailed report, you're not starting from zero. You're jumping halfway through the problem, and that's again the difference between reactive troubleshooting and efficient engineering-based troubleshooting. All right, now let's take a look at wireless health. Especially from a Meraki engineering level perspective. A powerful heuristics engine that rapidly identifies anomalies that impact the end user's experience across every stage of client connectivity for rapid root cause analysis and response. Okay? That's by definition wireless health. At a high level, it's not just a dashboard. It's a heuristics-based analytics engine, which allows us to continually evaluate client connectivity across its entire life cycle. That life cycle is the key. We're not just looking at, is the client connected? We're breaking it down to those stages that we talked about before. The association stage for RF and layer 1 and layer 2. The authentication stage for 802.1x and PSK. The DHCP stage for layer 3 addressing, DNS and application readiness at layer 7. But what does a heuristics engine actually mean? When they say heuristics, they mean a system that is analyzing patterns, not just looking at raw events. So instead of correlating radius logs and DHCP failures and roaming events, we do that automatically by looking at anomalies, looking at failure trends, and then looking at performance degradation. And this is how wireless health thinks. It's a client-centric, not device-centric model. Right? Traditional troubleshooting is what? Is the AP up? Is the controller reachable? Whereas Meraki is saying, well, what's the client actually experiencing? So every connection attempt is tracked as a transaction. And it will get classified into 3 categories: success, failure, or degraded. And then we'll also break it down further by the stage. Is it an association? Is it an authentication? Is it related to DHCP, or is it related to DNS? All right, so instead of asking what's broken, we're saying, hey, where is it breaking? If we see high numbers of association failures, that could be related to an RF issue. Maybe we're having a convergence problem or interference. If we see high authentication failures, maybe that's a radius issue or maybe some sort of credentialing issue. If we see a high number of DHCP failures, maybe it's an IP addressing or relay issue. Again, jumping straight into the correct layer. All right, the interface also allows you to pivot across different dimensions as well. We can look at per client, we can look at per SSID, per access point, per time window, and we can answer questions like, is this a single user issue or is it widespread? Is it tied to one AP or the entire radio frequency domain? Did it start after a configuration change? What we're trying to reduce from an operational standpoint is our MTTR, because we're collecting logs normally manually, we're correlating time steps, we're guessing at a root cause. We're getting those pre-correlated insights in this case. Wireless health is built in, it's always on, and it's actually not even a licensed add-on. There's no deployment overhead. It's basically collecting telemetry from your MR access points, from your client sessions, and from your back-end services. We're translating from reactive investigation to proactive data-driven analysis, and it actually lets us troubleshoot based on actual user experience, not just looking at the health of the infrastructure. All right, now let's take a look at the wireless health flow here. This is actually one of the most important visuals in this entire section, right? Which is also important in terms of basically our wireless troubleshooting workflow. All right, so what Meraki is doing here is it's breaking down client connectivity into a deterministic sequence of stages. So instead of guessing where things fail, we can pinpoint the exact phase of a failure. This 4-stage client connectivity pipeline is what every wireless client has to successfully pass in order to operate, right? We have association, we have authentication, we have DHCP and DNS. At layer 1 and layer 2, we have our radio frequency. So the client discovers the SSID using beaconing and probes. It does an 802.11 association to the AP. Any kind of failure indication here would be based on RF interference, whether it's adjacent channel interference or co-channel interference, maybe a low RSSI or SNR value, or maybe channel utilization, saturation, or maybe the AP is reaching some sort of capacity limit. If this fails, the client never joins the network. Then we have our authentication, layer 2, AAA. This could be open authentication, pre-shared key authentication, using extensible authentication with 802.1x. And we have radius interactions for our enterprise WLANs as well. All right. Some of the failure indicators that we would see here is that the radius server is unreachable, or maybe it's misconfigured. We have incorrect credentials, or we have certificate issues, or maybe there's some sort of latency between the AP and radius, which is causing some EAP timeouts or something to that effect. This is where most enterprise Wi-Fi problems will actually take place. Then we see DHCP, which is layer 3 addressing. The client sends a DHCP discover. It receives an offer, a request, and then ultimately an acknowledgement. Some of the failure indicators that we'll see here are DHCP scope exhaustion. Maybe there's an issue with IP helper, which is our proxy, our relay configuration. Maybe there's a VLAN tagging mismatch. Maybe there's a firewall that's blocking UDP, port 67 and 68, boot PS and boot PC. So the client's connected, but it doesn't have any IP address, which means no internet, no intranet. That's kind of the symptom. Then we have our DNS resolution, which is our layer 7 readiness. So we're trying to resolve maybe a fully qualified domain name to an IP address. Maybe that DNS server is not reachable. Maybe it's the incorrect DNS configuration in DHCP. Maybe there's a split horizon issue, internal DNS issues, and so on. A lot of times, this type of issue is mistaken for the internet is down because I can't resolve things on the internet, but actually it's just a DNS issue. Why does this visualization matter? What you're seeing is a graph which is a progressive drop-off model. Each stage shows a percent of clients entering, the percent that are successfully passing, and the percent that are failing at that step. So this gives you what we call a failure funnel. So let's say the association is 98%, but authentication is 76%. we immediately know that the radio frequency is fine, the RF spectrum is fine. The problem is related to AAA. So we don't need to check cabling. We don't need to analyze the radio frequency spectrum. We don't have to debug our switching. We go straight to the radius logs. There is some advanced interpretation here as well. We don't just look at the percentages. We will look at where the biggest drop occurs. A large drop between association and authentication clearly points to some sort of AAA security-related issue. A large drop between authentication and DHCP or layer 3, VLAN, whatever, that's going to indicate maybe a DHCP issue. All right. If there's a clean pipeline, but the users are complaining, now we're starting to say, okay, then it's got to be something related to an application, or maybe it's a WAN issue, or maybe it's some sort of upstream issue. The correlation with the infrastructure is critical here. This is where experienced engineers take it to the next step. We now correlate this with AP level metrics, CPU and channel utilization, switch port and VLAN trunk configurations, DHCP server logs, radius response times, and so on. So wireless health gives us a starting point. It's not the full answer, but it gets us where we need to go more quickly. We need to be proactive. Absolutely. And this again is related to wireless health analytics. This is where we move from troubleshooting to engineering that network ahead of the problem. Most administrators live in a reactive world. In fact, we really can't get away from it entirely. We can try and plan away from it as much as possible, but there's always going to be some level of reaction. And that is the user reports an issue and we run like crazy to go fix it. At scale, that doesn't work because you're constantly fixing problems. So Meraki Wireless Health gives us the ability, based on data-driven optimization, to be proactive. So instead of waiting for failures, we're constantly analyzing the connection success rates, the failure trends, the client experience metrics. And we're asking ourselves, okay, where will the next problem likely occur? So we can see things like total connection attempts versus failures. We can see the failure rates by stage, whether it's by association or authentication or DHCP or DNS. We can see the worst performing access points. We can see the worst performing client types. And that's critical because not all of the problems are going to be infrastructure related. It could be a specific operating system, or maybe a patch was applied that caused problems, or a specific driver, or maybe it's even a specific device type. So identifying the problem areas. Is it the AP? Is it location based? Notice we have a visual layout here with APs. We can map performance geographically across our entire deployment. That allows us to identify radio frequency dead zones, maybe high density contention areas, because again, radio frequency spectrum is layer 1, misconfigured APs. We can see, for example, that one AP might be showing us a high failure rate, which would indicate probably a local issue, or we could see multiple APs in a zone. So that's going to be more related to maybe an RF design issue. We can also look at client type analytics. And this is a big one, right? We see worst client device type, the middle one there. So if we see Windows 10 devices failing authentication or iOS devices failing DHCP, that's probably not random. That is a pattern-based failure. So we have to look at our radius policies. We have to look at our DHCP scopes and our options. Maybe there's a device compatibility issue. So it's optimization versus troubleshooting. Instead of the Wi-Fi is broken, you're optimizing your connection success rates, your roaming performance, and the latency and user experience. In my experience, my personal experience, there's always kind of these 3 questions that you should ask yourself. Are the clients connecting successfully? and look at that end-to-end success percentage. Can the experience be improved? Right? We're not talking about, yay, this is fun, but we're talking about the overall performance experience. We're looking at retries and latencies and failures in each stage. And then can the wireless LAN design itself be optimized? Environments are constantly changing. You might see a situation where an office looks like something one day, and then they add partitions, or they move around cubicles, or they bring in new equipment or whatever, and it changes completely how the frequency spectrum operates. And we're also talking about even just advances in the wireless technology as we move from Wi-Fi 5 to Wi-Fi 6 and so on. It changes our channel planning. It might change our power levels. It could change our AP placement. So we always have to kind of reevaluate it. Signal to noise ratio matters as well. All right? Slow data rates are almost always tied to a signal to noise ratio. We'll take a look at that right now. All right, so here it is. Slow data rates, check that signal to noise. All right, one of the most misunderstood but most critical concepts in wireless networking, that old SNR, signal to noise ratio. If your users are complaining about slow Wi-Fi, buffering, poor performance, this is usually where you're going to look first. All right? By definition, SNR is the difference between the received signal strength and the noise floor, and we measure that in decibels. Think of it like you're in a room communicating to a bunch of people, and your voice is the signal, and nobody else is talking, so your noise floor is very low. But now take that room from like a meeting environment to a social gathering. All of a sudden, everybody's talking. And what has to happen? You have to speak louder. You have to repeat your information because the noise floor is competing with the signal. All right. So how clearly can you hear the signal over the noise? The graph is showing us what we've got. The green line is our RSSI. That's our signal strength indicator. The red line is our noise floor, and the gap between them is the ratio. The bigger the gap, the better the wireless performance. The smaller the gap, the poorer the performance. But here's the mistake that people will make. They tend to focus on signal strength only. If you have great signal strength, but you have really bad SNR, doesn't matter because the noise is as powerful as the signal. And from a client's perspective, it all looks like signal. All right? There are two main ways that the SNR will degrade. Weak signal, so the client is too far away from the AP, we have a low transmit power, we have poor antenna placement, something like that. Or, which is even worse because it's a lot more difficult to fight because it's not really based on design or implementation, is that high noise floor. Microwaves, Bluetooth, neighboring Wi-Fi interferers, radio frequency interference, co-channel interference, too many access points on the same channel, high channel utilization. And this is kind of where most enterprises sit. SNR actually determines what modulation the client can use. If we have a higher SNR, that means we have a high MCS index, which means we can operate at faster data rates. Lower SNR means lower modulation, which means slower speeds. Now, this isn't a wireless engineering class, so we don't necessarily need to get into those specifics, but there is a direct correlation. All right? The client basically has to step down. So even if you're connected, even if DHCP is working or DNS is working, you're still getting poor performance because the client is operating at that poor level. There are some real targets that you should know. Around 20 dB SNR is minimum for usable data. By the way, the larger the number, the better, right? So around 25 dB, that would be typically recommended for voice over IP. 30 dB plus, excellent performance. So anything below 20 dB, you're looking for retransmissions, latency, poor throughput, stuff like that. There are some tools in Meraki for this visibility. There's the client details page, which shows real-time SNR per client. We can see in this case 40 dB, which is really good, right? That helps allow us to identify client-specific issues. And then we also have the RF spectrum analyzer, which is built in. That shows us our noise floor trends. It shows us our channel utilization, our interface patterns, interference patterns, I should say. And this is how we differentiate between weak signal versus a noisy environment. All right? When I'm trying to teach troubleshooting, say, slow Wi-Fi, the first thing I need to do is check the wireless health. Check the client SNR. And if that SNR is low, then I start to look at RSSI, maybe coverage issues, or maybe I check the noise floor. That's my decision tree. So let's say the user comes to you and says, hey, the Wi-Fi is slow, but I'm connected. All right, so association good. Authentication good. DHCP good. All right, but then we go out and check the SNR and it's 12 dB. That's a little bit of a problem. SNR is the single most important radio frequency metric for performance. Connectivity does not equal performance. SNR determines the performance. All right? Performance and stability issues, check the channel utilization. So SNR tells us quality. Channel utilization is going to tell us congestion. And that's where a lot of wireless networks fall apart, especially if you're dealing in a dense environment. So what is channel utilization? It's the percentage of time the radio frequency medium is busy. It's literally not just your traffic. It's all the traffic that the AP can hear. The clients, the neighboring APs, rogue devices, non-Wi-Fi interferers. And if the channel's busy, guess what the client's going to have to do? The client's going to have to wait to transmit. Remember, Wi-Fi, and we talked about this in one of our previous modules, is half duplex. It's contention-based. Only one device transmits at a time per channel. All right? So if the utilization is high, that means more waiting, more back-off timers, more retransmissions, and that result is going to be slower performance even if you have a perfect signal. So what are some of the typical symptoms that we see for high channel utilization? If it gets too high, we'll see slow network performance, intermittent connectivity, packet loss or retries, clients are struggling to join the network, or we could have missing SSIDs. Beacons get delayed or dropped. Very, very classic congestion indicators, not RF coverage issues. There are actually three main categories that cause high channel utilization. One is co-channel interference, which we tend to call CCI. Too many APs on the same channel, or maybe we have overlapping coverage cells. Too many clients, meaning a high density environment, so everybody's kind of sharing the same airtime. That's a real resource. It's not bandwidth, it's a real resource. And then excessive broadcasts or maybe management overhead. Too many SSIDs. Low data rates are enabled. Legacy clients are dragging down the efficiency of our wireless network. So what are the remediations? We can do better channel planning. Use non-overlapping channels in the 2.4 gigahertz spectrum. 1, 6, and 11. Avoid excessive reuse in the same physical space. Raise the minimum data rates. Get rid of the lower data rates like 1, 2, and 5.5 megabits per second. That means that's going to force the clients to transmit faster, which means they're going to use less airtime. Faster transmissions, less channel occupancy. We can also adjust the cell size. A lot of people look at this and go, lower the power? Why would I lower the power? That's going to decrease my coverage area. Absolutely. We're trying to shrink the coverage cells so we don't have as much density, and maybe we don't have as much overlap. So we're going to get less co-channel interference. We also try to limit the number of SSIDs. Every single SSID adds beaconing overhead. Beaconing happens about 10 times per second per AP? So maybe keep it around 3 to 6 SSIDs at the most. We also want to be able to check for rogue APs, detect rogue APs and interference. Use a spectrum analyzer, identify those unauthorized devices, or even external RF sources, and hopefully you can come up with a solution to get rid of them. And then we can also do traffic analysis. We're looking for high volume traffic like streaming or backups. We can apply QoS policies or shaping policies. Most of my Meraki APs include a dedicated dual band scanning radio, meaning they can monitor the RF conditions, they can measure utilization, they can detect interference, and it's not going to impede or impact the client traffic. So now when that user says, hey, the Wi-Fi is slow, you check the wireless health, you check the SNR, you check the channel utilization. And now that becomes your layer 1 to 2 wireless decision tree. Remember, channel utilization is an airtime congestion metric. High utilization means high contention, high delay, and crappy performance. Even if the signal is strong, even if authentication is working, even if DHCP is working, it doesn't matter. We can also track security threats with Air Marshal, which is essentially Meraki's WIPS. All right? So now we're getting away from performance and looking at wireless security. And that's where Air Marshal sits. Air Marshal is basically a wireless intrusion prevention system that's built directly into the MR platform. It runs off the dedicated scanning radio, so it's always monitoring that RF environment, but it doesn't affect your client traffic. I mean, at a real high level, it's passively scanning all the channels. It's trying to identify unauthorized or suspicious RF activity, classifying threats based on those behavior patterns. We're not just detecting APs, we're actually analyzing the 802.11 frame behavior and the patterns. And there are some core threat categories. In fact, Air Marshal will actually group wireless threats into 4 major categories. And these are the 4 categories that we see here. Spoofs, someone intentionally impersonating your network identity. We call this an evil twin attack or an impersonation attack. Someone's trying to pretend to be your network. They're using the same SSID. They're using similar or identical BSSID patterns. They're basically trying to trick clients into connecting. So instead of having like a corp Wi-Fi, maybe they have a corp dash Wi-Fi. Or even the same SSID, but using a rogue AP. This is used to do things like credential harvesting or facilitating some sort of man-in-the-middle attack. Rogue APs, list of rogue APs in the nearby vicinity, and those identified as being on the wired LAN. All right? What they're describing here are two different types of rogues. Regardless of rogue AP, shadow IT, unauthorized APs detected in your environment. You can have external rogues, which are nearby, but they're not connected to your network. Or you can actually have internal rogues, which are actually plugged into your network. Those are clearly a lot more dangerous. That means you're essentially suffering a direct security breach. Packet flooding for denial of service. Clients on an AP that are sending an excessive number of packets to your AP. Right? DOF floods, probe floods, association floods. The idea of those types of attacks is to overwhelm the network, cause outages, basically denial of service. And then we have malicious broadcasts, DOS or DDoS attacks that attempt to prevent clients from associating with a legitimate AP. In our RF space, by the way, so we're trying to prevent clients from associating, or we're trying to disrupt normal WLAN operations. Mostly that's tied to a deauthentication attack, but it could also be radio frequency jamming as well. So how does Air Marshal detect these types of threats? It looks at the beacon frames, it looks at probe responses, it looks at authentication attempts, deauth and disassociation frames, and it's looking for anomalies like duplicate SSIDs that have different RF signatures, abnormal frame rates, unexpected MAC behavior, and other things, right? Anomalous behavior. All right? Detection provides us the ability to identify the threat. Containment allows us to actively stop it. So Meraki will give you alerts, and it will even classify the threat. But you can also contain rogue APs. Now, the way we contain a rogue AP is we just stop people from associating to that AP by sending deauth frames. We're not really technically getting rid of the AP. It's still there. We're not going to jam the radio frequency signal because that would be an attack against ourselves as well. We're just going to try to prevent other people from connecting to that device. But I will tell you that containment can be disruptive. So you have to be very careful about doing that containment in a production environment. In a modern environment, you actually don't control the radio frequency. You have neighboring businesses, you have personal hotspots, even unauthorized devices, but we're using the ISM bands, the industrial and scientific and medical bands, which are open frequencies. They're non-licensed bands. But at least Air Marshal will give us visibility into everything happening in that radio frequency domain. We're turning our APs into security sensors. All right. Now we've identified the threats. We're using Air Marshal. What do we actually do about them? All right. The reality is this is where theory kind of merges into operation. Detection is pretty easy. Responding and mitigating is more difficult. So before we even go threat by threat, Air Marshal can assist with containment. But the real mitigation involves physical validation and some sort of physical remediation. There is no kind of one button to fix the situation in Meraki. So what about the spoofs and the evil twins? First, these are impersonation attacks. So there is a risk of credential theft, man in the middle. We use Air Marshal to identify and classify those spoofed SSIDs. We could attempt containment, meaning that we're deauthing clients from that rogue AP. But then the critical step is we need to figure out where that device is. And that will require things like RF triangulation, walking the floor, maybe using a handheld tool like a spectrum analyzer. If you don't fix the spoofing from the dashboard, which usually you can't, you can kind of mitigate the potential damage, you have to track it down. Same thing with rogue APs, especially if they're connected to your wired network. Air Marshal containment will deauth the clients but that doesn't really get rid of the rogue. Switch side validation will check MAC address tables, and we might even be able to trace the switch port that the device is connected to, and then we physically disconnect or shut down that port. Also, remember, we do have shadow IT. Not all rogue APs are there for malicious intent. They're just not authorized to be plugged into the network. Containment is also dangerous in terms of legal implications. You cannot interfere with external networks. I had a situation with a customer many years ago where they were containing Starbucks AP, and that Starbucks wasn't even trying to spoof or evil twin their network. They just had an AP, and the network engineer thought, well, they're taking up our frequencies, so let's contain them. And they actually got a letter from the FCC saying, hey, you can't do that. This is an open band, right? As long as they're not transmitting above EIRP of 100 milliwatts, and you can't block them. All right. Packet floods, usually volume based, so deauth floods, probe floods, etc. We can certainly use the dashboard to identify the source of those floods, maybe the MAC address. And then if it's a misbehaving client or maybe a malicious tool, we can isolate it down to a switch port or do some sort of client blocking. But ultimately, we need to locate and remove the source device. And then lastly, malicious broadcasts, some sort of denial of service, RF-based attacks. Again, our goal is to prevent association or to disrupt connectivity. So we identify the RF source using Air Marshal, and then we correlate that with client failures, with association or authentication drops, and then we apply containment, but we do it with caution. All right? And ultimately, again, physical identification and removal is the real world fix here. All right? So again, think of this best practice approach as detect and classify, which we use Air Marshal, contain if appropriate to give us temporary mitigation or control, and then physically remediate. That's our permanent fix. If you ultimately skip step 3, the problem's going to keep coming back. So I suppose the biggest key takeaway here is that this is not the end-all be-all solution, but it's great for understanding the RF behavior and for correlating events and then physically removing the threat from your environment. All right, last thing in this section here, and this is kind of important as well, the entire wireless troubleshooting flow, right? If you don't understand this flow, then you're probably guessing, right? So we're going to break this down into 3 parallel processes. Clients connecting to the AP, DHCP, and 802.1x authentication if it's being used. You have to understand both the order and the dependency of each step. So let's start with association, which is our layer 2 connectivity. Everything starts with association. The client discovers and then joins the AP at layer 2. We get a probe request, a probe response. By actively scanning, we get beacon listening by passively scanning, and then we send an association request and we get an association response. All right, at this point, the client's connected to the AP, but they don't have any network access. If this fails, could be an SNR problem, interference problem, maybe the wrong SSID, maybe an AP misconfiguration. Step 2, authentication, including 802.1x and other security mechanisms. This is where the user's identity is validated. Now, in an 802.1x environment, it's a little bit more complex, right? We're running extensible authentication protocol over the LAN, meaning that's going to start with an EAP request from an AP or from an authenticator. We'll then get an EAP response from the client, which is our supplicant, and then that gets encapsulated inside of Radius and sent to the AAA server as an access request. Radius sends an access challenge saying, hey, I need your credentials. And then radius ultimately will provide either an access accept or an access reject. So any kind of EAP success means that the client is authenticated. If it fails, it could be because the radius server is unreachable, you're providing bad credentials, there's a certificate issue, there's some sort of time mismatch, which can be an issue for 802.1x because certificates are time-based. But no successful authentication means no DHCP, no IP, no network access. Then we have step 3, which is DHCP, our IP address assignment. Once authentication succeeds, now the client can request an IP address. This is our classic DORA process. A DHCP discover from the client, which is a broadcast, a DHCP offer from the server, which could be a broadcast, but it could also go to the client. A DHCP request from the client, again, could be a broadcast. And then a DHCP acknowledgement. Once all that happens, the client gets an IP address, a mask, a gateway. They get their DNS information. But if it fails, it could be related to a DHCP scope exhaustion, a VLAN mismatch, IP helper issues, blocked UDP ports like we talked about before, 67 and 68. Okay? DNS, the application layer. This is our final step, DNS resolution. The client translates the names into an IP address in forms of DNS queries, and then we get a DNS response. Then we can use the network. So maybe the DNS server is not reachable. Maybe the wrong DNS servers are configured. There could be possibly a firewall blocking DNS. All right? So lots of things to consider. If we put this all together, this is the mindset I want you to have. Every step depends on the previous one. We can't trouble DHCP if authentication fails. We can't troubleshoot DNS if DHCP fails. So your troubleshooting flow should always be association, RF layer 2, authentication, security AAA, DHCP, IP address assignment, and DNS application reachability. All right, now we're moving back up the stack. Up to this point, we've been focusing on radio frequency, we've been focusing on client connectivity, infrastructure, but here's the reality in a production environment. Users don't complain about Wi-Fi, they complain about their applications. They say, I can't get to Salesforce, or Salesforce is running slowly. The web application isn't loading. My Teams keeps dropping. And this is where Cisco Meraki Insight comes in. All right? Cisco Meraki Insight is designed to answer a very important question, which is, where is the problem? Is it the client? Is it the LAN? Is it the WAN? Or is it an application server? If we don't have that visibility, we're basically just guessing. A critical concept to this is end-to-end visibility. Look at the flow on the screen. We've got user to LAN to MX to WAN to server, which is our web app, and Meraki Insight analyzes that entire transaction, the HTTP request, the HTTP response, and if it breaks, it's going to break down the performance across each one of those segments. The LAN performance, the WAN performance, and ultimately the server response time. Now let's talk technically about what's happening behind the scenes. The MX appliance is acting as a collector. It's doing deep packet inspection on the HTTP or HTTPS traffic, HTTPS being port 443 and HTTP being port 80, and it's extracting things like latency metrics, round trip times, server response delays, application performance data, and then that metadata is collected and sent to the Meraki cloud using a TLS encrypted syslog message over TCP port 6514. This is not a full packet capture. It's metadata-based analytics. So it's very lightweight and it's highly scalable. All right, there are no synthetic probes. Something very important here. Meraki Insight does not use synthetic probes. We're not running fake test traffic. We're not simulating transactions. We're actually analyzing real user traffic, which means that we're analyzing the actual user's experience, real world latency, true application performance. What problems can we identify? Is the LAN clean? Is the WAN clean? In this case, yes, but the server is slow. So guess what? It's not your network. That's going to save you hours of troubleshooting and, well, probably stop some of the finger pointing as well, right? There is some performance impact and there are some design considerations. The performance impact is actually relatively minimal on the MX because we actually don't even need span ports. We're not using external collectors, so we're not running any overlay tunnels or anything like that. But as a best practice, we probably should track less than 10 critical applications at a time. We can actually support up to 50 at a time, but we want to make sure that our analytics are focused, that the analytics are meaningful, and that they're actually providing us information that's actionable without paralyzing us by looking at too much data. Now, another thing we have available to us is also voice over IP health, right? We're talking about application performance, but one of the most sensitive workloads in the network is our voice over IP traffic. Users are kind of a little bit more accepting about slow web applications. But if they get a bad phone call, that's it. So VoIP Health is actually part of Meraki Insight. It's monitoring and measuring call quality across every path from your network to the VoIP servers. That includes your ISP uplinks, your WAN paths, any path that you might have to a SIP provider or a PBX. So instead of guessing, we're getting quantifiable voice quality metrics. Now, this is a little bit different from normal Insight because we're doing active monitoring. We're actually sending ICMP probes every second from the MX appliance to the voice over IP endpoints. So with application analytics, we're passive. This is not passive. We are, in fact, doing synthetic testing in this particular case. What are we measuring? There are 4 critical parameters that we're trying to measure. You can see them listed in the column there: loss, latency, jitter, and then the ending result is some sort of mean opinion score. Well, that's a measured value as well. So latency is our end-to-end delay. And again, our target is typically around 150 milliseconds one way. Jitter is the variation in delay between the packets. That's what causes choppy audio. And our target there is somewhere less than about 30 milliseconds, right? So you see some of the ones that are unhealthy, right? Well, they're mostly unhealthy because of packet loss. But we do see some like some that are hitting like 930 microseconds. That's clean, right? Don't confuse microseconds with milliseconds, right? We're also trying to track packet loss. Of course, 100% packet loss, well, that's going to result in obviously poor quality. But we're looking for missing audio. Well, that's the result of packet loss. And our target is about 1% or less. The mean opinion score is a scale of 1 to 5. That represents the perceived call quality for that voice over IP call. And technically anything above 3.9 in at least Cisco voice over IP networks is considered toll quality, but 4 is a good number to work with, right? Anything above 4 is good. 3.5 to 4 is moderate, and then anything below 3.5 is bad. The MOS value combines latency, jitter, and packet loss into a single score that represents what the call quality would actually sound like to a user. So instead of looking at raw metrics, we're actually getting kind of a human experience score. Okay? What does the problem solve? In a voice over IP network for health, we're trying to answer two critical troubleshooting questions. Is the network causing poor call quality? If not, where is the issue? So if we have a low mean opinion score and the WAN metrics are bad, that's probably a network related issue. If not, then why is the MOS score still low? It could be the VoIP provider, it could be the SIP server, it could be the upstream carrier, and so on. All right? All right. Now, here's where things get really powerful. Up to now, VoIP health is basically telling us there is a problem somewhere along the path. But this feature, this hop-by-hop analysis, tells us exactly where the problem is. All right, so we're going from general visibility to pinpoint accuracy. It does a path level breakdown between the MX appliance, the ISP, the internet, and ultimately your VoIP server. It is traceroute based analysis, but it's enhanced with things like MOS scoring, packet loss, latency, and jitter at each individual hop along the path. So traceroute gets initiated with the built-in traceroute tool that comes from the MX towards the voice over IP endpoint. Each hop is probed, every router along the path responds, and metrics are collected per hop. The MOS value then gets calculated per hop based on latency, jitter, and packet loss, and then all of our thresholds get applied. Anything with a MOS of 3.5 or below is flagged as bad, and then that's going to immediately highlight a problem segment. Okay? Why is this important? Normally, troubleshooting in the WAN is, it's a problem with the ISP. It's a problem with the VoIP server. It's a problem with the provider. It's not our fault, it's their fault. But the hop-by-hop analysis says, okay, hop 2 is clean, that's our ISP edge. Hop 3, 5% packet loss, and that's where our MOS drops below 3.5. So it's evidence. It's not finger pointing, it's not an opinion, if you will. All right? So when you look at the table, each row equals one hop, and you're going to see an IP address, a domain, a MOS score, packet loss percentage, latency, and jitter. And you're looking for sudden jumps in latency, or maybe spikes in packet loss, or some sort of MOS degradation. All right, the first hop is where the metrics are actually degrading. That's most likely our problem location. See a 5% packet loss, 6.4 millisecond jitter, although we are hitting 8.6 in the last hop. But let's say hop 1 is the MX and it's clean. Hop 2 is the ISP edge and it's clean. But hop 3, which is our upstream carrier, we have a 6% packet loss. All right. It's not reflected in this diagram, but that's, a way of looking at it. That tells us instantly that our LAN is good, our ISP handoff is fine. The issue is upstream, either peering or with the carrier or something like that. And then we can escalate with the evidence instead of just saying, hey, it's your fault. Okay? This is huge for things like ISP troubleshooting, for SLA validation, for SD-WAN path selection, VoIP provider escalation. You're no longer just saying, hey, the calls are bad. You're literally saying, hey, at hop 4, which is you guys, the MOS dropped to 3.2, because of a 3% packet loss. Very, very useful. All right, now we're going to shift gears a little bit. We're away from our kind of wireless troubleshooting and everything else, and now we're going to get into troubleshooting Meraki Auto VPN. And there are multiple phases that we go through, and we'll take a look at those in, 7 or 8 different slides that we're going to take a look at in this section here. But this topic seems rather simple when it comes to Meraki, but under the hood, there's a lot of stuff happening. And if you don't understand the phases, troubleshooting Auto VPN is difficult. So let's start with the registration phase. Auto VPN actually has 2 major phases. The registration phase, which is what we see here, and then the connection phase. That's where we actually establish our tunnel. If registration fails, then we're never going to get to that second step. So this step is always something that has to happen. So what's actually happening here? The MX is basically saying, here's who I am, here's how to reach me, and here's the networks that I have. And then it sends that information to the VPN registry in the cloud. We talked about this previously in another section where we were talking about Auto VPN. Now, in this case, we actually have 2 different VPN registries. This is for high availability for fault tolerance. If one registry fails, then the other one still maintains those VPN mappings. So each MX sends a public IP address, a UDP source port, and the advertised subnets. HQ 1.1.1.1, port 50,000, subnets A, B, C, and so on. Branch 2222, port 60,000, subnet Y. And this is basically how each site learns how to reach the other sites. Port behavior is testable, and it is somewhat predictable. The destination port is always UDP 9350, communicating to the cloud registry. That doesn't change. Remember, we talked about this before. The random source port is anywhere from 32,768 to 61,000. Why is this important? Because we know that firewalls have to allow outbound UDP 9350. The NAT devices have to allow that return traffic, because this is where things typically break. Now, what happens after the registration? Once both sites register, then the registry shares that information between its peers. HQ learns how to reach the branch, and the branch learns how to reach the HQ. And then this is the precursor to set up the VPN tunnels in the next phase. Now, if Auto VPN isn't coming up, where would I typically look first? Now, my first step would always be to say, hey, can the MX reach the registry? So check that outbound UDP 9350, make sure it's allowed. Make sure you have DNS resolution. Make sure you have, of course, internet connectivity, whereas that probably would be something that would be discovered prior to this. And then also make sure you don't have any NAT-related issues. Symmetric NAT can cause problems. Port translation inconsistencies can cause problems. And certainly if you have firewalls that are blocking high UDP source ports, that can cause a problem as well. So when we're troubleshooting, if the MX is not registered, then no tunnels will form. We need to validate registry connectivity, public IP visibility, and make sure that we're advertising the correct subnets. All right, now let's get into the connection phase. Registration is complete. Now we have to build the tunnels. We're transitioning from registration to connection, meaning that the MX devices are registered. They've learned everything, IP address, UDP port, subnets. Now they're ready to form their direct peer-to-peer tunnel. So in step 1, we pull the peer information from the registry. Every MX goes back out to the VPN registry and says, who do I need to build my tunnels to, or with, or whatever. And then the registry is going to respond with the peer public IP, UDP port, advertised subnets. That is all control plane behavior. But we are transitioning into setting up the data plane. Step 2, the direct peer-to-peer tunnels. Right? Remember, Meraki Auto VPN is not hub and spoke through the cloud. We form direct tunnels between the peers, MX to MX. So traffic doesn't have to hairpin through the cloud. The cloud is the orchestrator. It kind of manages that, but it doesn't carry the actual data. Now, we talked about this concept previously before as well, which is UDP hole punching. It's critical because most MX devices are behind NAT devices. So how are they going to connect? Both sides have to simultaneously send UDP traffic to each other. HQ needs to go to the branch at destination port 60,000, and the branch needs to go to HQ at destination port 50,000, which means that's going to open up a NAT translation on both sides, which hopefully will allow that return traffic, which means that we can establish our bidirectional flow. That's essentially what hole punching is, UDP hole punching. Then the last step is our tunnel formation. We do our AES encrypted IPsec tunnel. Now, it's not traditional IPsec. It's kind of IPsec-like, if you will. Meraki actually abstracts traditional IPsec constructs. There's no manual IC config. We don't have to configure transform sets. We don't have to set up crypto maps. But it's all happening. Encryption, key exchange, secure encapsulation. It's still happening. We're just not having to manually configure it. It's an abstracted configuration. Then the step 4 is route exchange. The routes also get exchanged automatically. The subnets are configured in the dashboard, and then they get advertised across the VPN. Those routes actually go into a separate routing table for VPN routes. So we have the clean separation from the local routing, and that also gives this the ability to apply easier policy control. So there are some common failure points here. If the tunnel doesn't come up, maybe I look at NAT issues like port translation inconsistency or symmetric NAT, which breaks hole punching, firewall blocking, meaning UDP ports are being blocked or those high ephemeral ports are being blocked. Maybe there's some sort of ISP restriction using CGNAT, like carrier grade NAT, or maybe the UDP timeouts are too aggressive. We could have incorrect subnets being advertised. Maybe networks are missing, or we have overlapping subnets. So there are some considerations to take into account there as well. So let's kind of break it down into even more detail, all right? Where we're kind of matching this config scenario to possibly issues that might come up. AutoVPN is actually designed to just work. If it doesn't, in my experience, I've seen that it's almost always something outside of the MX. So what this slide is showing us is that when you're looking here at the registration phase, there's a registration failure. The MX is trying to reach the VPN registry, but that communication is failing. It's pretty obvious probably what that's going to be. The outbound UDP port 9350 is being blocked. All right. AutoVPN cannot function without registry communication. Very important. So it could be blocked by a firewall. It could be blocked by an ISP. It could be blocked by some sort of other upstream security device, but that's definitely going to break registration. During the registration, that MX is sending traffic with that source random ephemeral high UDP port number, and then a destination for Meraki registry of UDP 9350. All right, registration is our control plane foundation. If the control plane fails, no peer discovery, no route advertisement, no tunnel formation, and so on. So again, we need to check if there's an upstream firewall, some sort of ISP filtering, misconfigured NAT devices, security appliances that are in the path, and so on. How do we actually troubleshoot this? In the dashboard, we would look for something like VPN registry unreachable or failed to connect to registry. Then we can start to do our test connectivity. Can the MX reach the internet? Is DNS working? Go back and check your firewall rules for outbound UDP 9350, and then even look for return traffic. Maybe and then start doing some packet captures, but ultimately we need to allow UDP port 9350. Is there a solution? Yeah, I mean, it's kind of a subtle failure here. It's not really a big thing to do. In this case, nothing is actually outright blocked. So traffic is flowing, but it's still not working. Something's not working. The MX is reaching the VPN registry. UDP 9350 is working, but there's a problem. That source UDP port is being changed by an upstream device. That could be a load balancer or maybe some other device that's doing NAT. So it's being changed from 9350 to 54321. That's what we call port address translation or port rewriting. It's a big problem, right? The MX tells the registry, here's my public IP, here's my UDP port, and then the peers rely on that information to communicate. If we're changing the source port or we're using some sort of different translation per flow, then everything becomes inconsistent with conflicting entries. So the peers try to connect using incorrect port information. That tunnel establishment is going to fail. The dashboard will typically say something like NAT type unfriendly. Not all NAT is equal. Friendly NAT would be NAT that does consistent source port mapping. We use the same external IP and port. It gives us predictable behavior. Unfriendly NAT means that the source ports are changing per session. We have multiple public IPs that are being used or symmetric NAT behavior, and that's going to break peer-to-peer communication. There are some real-world scenarios that can cause this to happen. Carrier-grade NAT is a perfect example. If you're running some sort of dual NAT environment, or if you have some aggressive port address translation on a device, or even if you're doing load balancers with source NAT, right? Different outbound flows get different translations. The fix is really not, something that we can always control, but it's always about NAT consistency. The best fix is one-to-one. Same public IP, same source port. We're not rewriting the session. All right? If we can configure our load balancers or our firewalls to preserve the source ports, get rid of that randomization, that would help. Avoid SNAT if it's not needed, or put the MX directly behind the ISP. Don't have a NAT device in front of it. All right, another example, AutoVPN. In this case, connection phase is blocked because of the UDP return traffic. Now, there are two different failures that we saw before, right? Registration works, peer discovery worked, but now, well, in the previous examples they didn't work, but now they are. And we're having an issue with the connection phase, where the tunnel should form, and it's not. So if you look at the flow, HQ and branch both have public IPs. They both have UDP ports. They both have registry entries. Everything looks good, but there's a firewall blocking traffic during the connection phase. So this isn't about UDP 9350 anymore. It's about peer-to-peer UDP communication between the MX devices. So the firewall is probably blocking return traffic, or maybe it's blocking dynamic UDP ports. Remember, AutoVPN uses 32.768 to 61,000 ephemerally. UDP ports, not fixed ports. So during the connection, no problem. They can set up the connection, HQ to branch and branch to HQ, because of the UDP hole punching process. But if the firewall doesn't allow return traffic or blocks those high UDP ports, or it doesn't maintain the state properly, then the NAT entry is never complete. We don't get bidirectional flow, and the tunnel's not going to establish. This is where it gets a little tricky, because you're looking at it and you're saying, I allowed the traffic, right? You have to allow outbound UDP, but also the return traffic. And most modern firewalls do that from a stateful nature. But you also have to allow that ephemeral port range. If the firewall is stateless or restrictive, the return traffic is going to get dropped, and hole punching is going to fail. So the best practice is allow those ports. Allow bidirectional flow between the peers. Make sure that the firewall tracks sessions and allows return traffic automatically. All right. Now, Meraki's recommendation is, instead of chasing ports, allow all outbound UDP and allow established or related return traffic. If needed, you can actually go to check dashboard and go to help and go to firewall info, and you can identify actual ports that are being used, and you can then in turn recreate explicit rules. So if we see registry success, if we see peers discovered, but we see the tunnel down, that immediately tells you that this is a connection phase problem. We have to have that bidirectional UDP communication for it to work. Now, another issue that we can run into is that the tunnel is up, the VPN is up, but traffic isn't flowing. All right, so we have a registration is successful, the connection phase is successful, the tunnel is established, but look at subnet Y. VPN is off. That's the problem here. AutoVPN has two major components. The tunnel formation, which is the control in the data plane, which we've been talking about, and then the route advertisement, which is what networks are actually shared. So in this case, the tunnel exists, but the route's not being advertised. So the traffic has nowhere to go. From HQ, it tries to reach subnet Y, but subnet Y is not participating in the VPN, which means it's not advertised, it's not going to show up in the VPN routing table, and it's not going to be reachable. All right, so everything in the dashboard looks good. It's all green. The VPN status shows connected, but the user says, hey, I can't reach anything. All right, and that's because the routing is incomplete. AutoVPN relies on explicit subnet participation. Each subnet has to be enabled for the VPN and advertised. If it's set to off, it's never going to be reachable across the tunnel. Pretty straightforward fix. Just go to security and SD-WAN, go to site-to-site VPN, change VPN off to on for whichever subnet's affected. Once that's enabled, the subnet gets advertised, routing table updates go through, and traffic flows pretty easily. Okay? You can probably recognize this pretty quickly because the tunnel is up, the registry's good, you're just getting packet loss at the tunnel level. So make sure you check subnet participation. Also, remember, AutoVPN is not just about tunnels. It's about what networks are allowed over that tunnel. All right, our final slide, I kind of call this the money slide, if you will, right? This is our entire AutoVPN troubleshooting framework in 3 different failure domains. Everything you see here falls into one of 3 buckets. A registry failure, which means our control plane is broken, disconnected registry, UDP 9350 is blocked, or there's some sort of NAT translation failure, So NAT type is unfriendly, or there's some sort of routing failure. The tunnel's up, but we're not seeing any traffic. All right. So the MX can't reach, say, the Meraki registry. Check for 9350. No registration, no peer discovery, no tunnels. So go back and fix that outbound UDP 9350 and then verify your upstream firewall rules. If this is broken, nothing else matters. Number 2, NAT type unfriendly. The middle scenario. A little bit more advanced. The MX can reach the registry, but NAT behavior is inconsistent. We need to check port translation, port address translation, especially the rewriting rules, multiple public IPs, or maybe some sort of symmetric NAT behavior. Here we're going to get incorrect peer info in our registry, or we're going to get tunnel information. The tunnels basically won't form, right? And the fix is to make sure that we have consistent NAT mapping. We use one-to-one NAT or static mappings. Try to avoid load balancers or anything that's going to rewrite the ports, or manually map ports if it's needed. This is not a reachability problem. It's a translation integrity problem. And then scenario number 3, the subnet is not accessible, the one we just talked about previously. The tunnel's up, traffic's not going. So that means the subnet is set to VPN off, meaning that the subnet's not advertised, there's no route across the VPN, traffic is going to fail. So go and fix that by enabling the subnet for that VPN participation. We do that under security and SD-WAN, and then we go to site-to-site VPN. All right? When I troubleshoot AutoVPN, I go in that order. Control plane. Can the MX reach the registry? Check UDP port 9350. NAT behavior. Is NAT consistent? Look for NAT unfriendly. Data plane and routing. Are the subnets actually being advertised? Check for VPN participation. If you follow that order, you will absolutely find or isolate the problem pretty quickly. AutoVPN problems are not random. They actually fall into these categories. And 90% of the issues you're going to run into are either 9350 is blocked, NAT rewriting ports, or the subnet's not enabled for the VPN. All right, our last topic is local status page. This is in a MX. All right, our last topic is the local status page. We're going to see this in our MX, our MS, and our MR. One of the most practical tools that you'll use in Meraki, especially when things are broken, the local status page. Think of the local status page as a direct local management interface to the device. Even if the cloud is unreachable, it's going to work. Meraki is cloud managed, but what happens when you can't reach the cloud? That page is your break glass in case of emergency troubleshooting tool. You can make basic configuration changes, you can check the device status and utilization, you can perform local troubleshooting, you can restore internet connectivity. Get me back online. That's your interface to do that. To access it, you don't even need to know an IP address. You can go to mx.meraki.com for the MX appliances. You can go to switch.meraki.com for your MS switched appliances, and you can go to ap.meraki.com for your MR access point. Okay? I don't know why they didn't just make them MX, MS, and MR, but anyway. Or you can actually go to my.meraki.com, or you can go to setup.meraki.com. All right, these URLs don't actually go out to the internet. The device intercepts that DNS request locally, and then it responds with its own local IP address. Internet access is not required. So it's a local DNS interception. The local web server is on the device, which means we get direct management plane access. We're bypassing the cloud entirely. Now, there is a bit of a gotcha, right? If you use my.meraki.com or setup.meraki.com, you're going to hit the very first Meraki device in the path. But that might not be the device that you're trying to get to. So use the specific URLs if you can. That will get you connected directly to the device. This page is absolutely critical if you cannot reach the cloud. Maybe you have a bad WAN configuration, an incorrect VLAN or IP address setting. Maybe there's some sort of DHCP issue, internet outage troubleshooting. If the dashboard is blind, this is kind of like your flashlight. All right. I would say even in real deployments, this is one of the first things I check, especially if a site goes completely offline. If I can reach the local status page, the device is alive. So that tells me that there's a problem upstream. Now, if I can't, I'm looking at a layer 1 or layer 2 issue. The cloud down does not mean that the device is inaccessible. We have the local status page, which gives us local troubleshooting access and a way back into our device. All right. There is alternative access as well. All right. What happens if things get really, really broken? DNS isn't working. DHCP is not working. I can't even resolve mx.meraki.com. What now? I still have access to the device. I can just go directly to its IP address. If DNS fails, Meraki gives you a fallback method. You can manually assign your laptop an IP address, connect to the device, and then browse to its local IP address. But your laptop has to be in the same subnet as the device, meaning that it has to have a static IP. So if the device is, say, 1.1.1.100, set your laptop to maybe 1.1.1.10 or 1.1.1.50 so that you're layer 2 adjacent. All right, for the MX security appliance, access is through the configured LAN IP. Of course, that you'd have to know that, but that's whatever you set in your dashboard. So make sure that that's documented correctly. In the MS switch, it's 1.1.1.100/24. That's the default. And in the access point, it's 10.128.128.126/24. This only works, though, if your client is manually configured in the same subnet. If you're not in the same layer 3 network, you're not going to work. This is absolutely your last resort. If DHCP is down, if DNS is broken, if there's a VLAN misconfiguration, if the device can't reach the cloud, you're doing maybe day 1 provisioning, this is how you recover that network. Okay? There is a real-world scenario as well. When you plug into the switch, you get no DHCP, you get no internet, you get no dashboard access. What do? Set your IP to 1.1.1.50 as an example. Open up the browser and go to 1.1.1.100. Access the local status page. Fix whatever needs to be fixed. You have to be physically connected, of course, as well. All right? Every Meraki device has a local interface, and you always have a path back in. As long as layer 1 or layer 2 is up, you're not going to be locked out. So our very last slide in this module is troubleshooting the local status page. If you know how to access the local status page, that's one thing. Knowing why it's not working is kind of advanced, right? There are 3 classic failure scenarios when you're accessing the local status page. It's disabled, the DNS traffic isn't hitting the Meraki device, or the MX is in pass-through mode. If you can actually disable the feature, the local status page feature could be turned off. you can disable it in the dashboard. And by the way, that's a feature that is applied network-wide. So you go to network-wide, you go to general, you go to local device status page, you can turn it off. The fix would be to re-enable it, but that might be a little bit of a problem if you can't get to the device anyway. All right. Second scenario is DNS traffic's not going through the MX. A little bit more subtle. So mx.meraki.com absolutely relies on intercepting that DNS by the MX. If DNS requests aren't going through the MX never gets a chance to respond. Maybe the client's using an external DNS server. Maybe that DNS server uses a different default gateway, or we're just simply bypassing MX completely. We need to make sure that the DNS traffic flows through the MX. All right. Or we're going to create some sort of manual DNS A record that points to the device's IP. If that packet never hits the MX can't help you. What if the MX is in pass-through mode? That's the right one we see here. So MX is basically acting like a bridge. It's not routing traffic. The local page, the local status page, I should say, is going to become unreachable, especially if the uplink subnet overlaps with the VPN subnets. The traffic is taking an unexpected path, or maybe it's only reachable through the VPN. So we would probably have to remove the MX from the VPN or access it through the VPN instead of locally. All right. So these are other three, the other three things that we would take a look at. All right. So we're going to wrap up this module, at least the learning piece. We've got 3 discoveries that we're going to take a look at: troubleshooting an offline device, troubleshooting content filtering, and then troubleshooting remote site connectivity.